At the start of this chapter, we went from a single integral to a double integral. A triple integral is next in the progression. Fortunately, the ideas themselves are not any more complicated. The only real challenge is the change of the visualization. When we had a single integral, we saw it as area under a curve. For double integrals, we saw it as volume under a surface. But for triple integrals, we don't really have any more space in our three-dimensional visualization to describe it geometrically. This forces us into a more abstract setting, where we're no longer thinking about a physical dimension, but simply as adding up the values of a function multiplied by the volume element. We'll start with the definition of a triple Riemann sum. This is a long definition, but everything functions pretty much the same way as it did with the double Riemann sum. The primary difference is that there's a third dimension floating around, so we have sub-boxes instead of sub-rectangles. In the same way as before, we would pick a point within each box and add up the function values multiplied by the volume of the individual boxes. And once we have this set up, all of the ideas from before can be pushed forward into 3 dimensions. When we take the limit as the size of the boxes go to 0, we convert this into a triple integral. The symbol dv is meant to represent a little bit of volume. Although this notation has a lot of symbols, you should be comfortable enough with the ideas that it's not too bad. We have 3 integrals because we have 3 dimensions to integrate. From here, we can look at our 2-dimensional ideas and see how they look in 3 dimensions. In 2 dimensions, we worked with areas, and in 3 dimensions, we work with volumes. The average value of a function on a region is the same idea, just replacing the denominator with the appropriate quantity. Notice that this fits with the pattern of previous formulas we had. To calculate the mass of an object, we just integrate the density multiplied by the appropriate differential element. The formulas for the center of mass generalize similarly, and you can look it up in the book if you want. At this point, we have observed that these formulas mirror our previous formulas. We have not actually talked about how to set up these integrals. Fortunately, it's conceptually the same as before, following the lower to upper mentality that we've developed. The only catch is that the lower and upper surfaces are more difficult to keep track of, and you really need to pay attention to what's happening. Let's look at example 11.7.5. Here, we are asked to find the mass of the tetrahedral region of a particular density. You can get from the equation of the plane to the graph by sketching the x equals 0 and y equals 0 traces, as well as the z equals 0 level curve. We're not going to worry about the integration part itself, because it's just a bunch of calculations that are worked out in the book. We're going to focus on the ideas for setting up the integral. The most intuitive way is to do the dz integral first. What this means is that you want to think about the lower surface and the upper surface. The lower surface is the z equals 0 plane, and the upper surface is the slanted plane. The book gives us the equation for this, which we need to put into form z equals something. The challenging part is to think about what this means for the remaining 2 integrals. The idea is to think about lines in the z direction that fill the region. What are the xy coordinates that you will need to account for all of those lines? In this case, it's the triangular shape at the bottom of the region. But that doesn't always mean it will be that. For each problem, you will need to think about where those vertical lines will be drawn to fill the volume, and use that as your guide. Another way to think about this is to view the picture looking down from the positive z-axis and look at the shape that you see from that perspective. I've found students to be a mixed bag with this, depending on just how comfortable they are with visualizing shapes in 3 dimensions. So you're just going to have to give it a try and see what works best for you. We still need to set up the integrals for the region in the xy plane, which requires us to find the equation for this diagonal line. That line comes from the intersection of the slanted plane and the z equals 0 plane, which gives us the substitution we need. In other problems, that boundary may be the intersection of other types of surfaces, so you'll just need to think carefully to make sure you can understand what's going on. But once we've reduced it to a 2-variable problem, then the setup should feel more familiar. If we do this as a dy integral next, we will have y equals 0 as the lower curve, and y equals negative x over 2 plus 3 as the upper curve, and the x limits are 0 to 6. Putting this all together, we get this as our integral, and we would still need to work it out. Fortunately, the integration steps are straightforward. You do need to work very carefully and cleanly, as small mistakes like missing a negative sign can be extremely difficult to locate and correct. Very few students find this to be easy the first few times. The book has multiple activities to help you with this process, and you're strongly encouraged to work through all of them. It's important that you take your time and think through everything carefully so that you make sure you really do understand what you're doing.